Ladies and gentlemen, welcome to the recitation, week 3 recitation. Well, in this recitation, I'd like to talk about some applications of vectors in geometry, since I didn't have time to do too many applications in the lectures. I think we have like a couple of lectures now, 3 lectures, and I want to do more applications of vectors. After this, there will be another recitation which will be offered by Jack, and he will solve a couple of two Putnam problems. Okay, first I'd like to go back to one of the problems that I didn't have time to finish during lecture, and that was the following problem. Let me restate it again. All right, so this was problem 1. Problem 1. This was a Putnam A3 in 1962. And okay, I'm gonna write the statement again. It was quite a long statement though, but anyway, I'm gonna write it again. So the statement of the problem said the following: in a triangle. Okay, I'm just going to write it the way it was written, and the way it appeared in the Putnam exam. So it says the following: in a triangle ABC in the Euclidean plane, let A prime be a point on the segment B to C, okay? B prime be a point on the segment from C to A, and C prime be a point on the segment from A to B. Okay. Such that we have the following ratio of segments, such that AB prime over B prime C is equal to BC prime over C prime A, and this is equal to CA prime over A prime B, and this is a positive number. Let's call this K. All right. And now we will consider a triangle delta. So let delta be the triangle formed by parts of the segments obtained by joining A and A prime, B and B prime, and C and C prime. Prove that the areas of the triangles delta and ABC are in the ratio K minus 1 everything squared over K squared plus K plus 1. All right, as you can see, the statement is quite long. but I think, well, I wanted to write it just the way it was in the Putnam competition. But in fact, let me draw a picture. I think if I draw a picture, everything is clear. And you will see that I will have a problem. In fact, I would like to, as I already explained in the lecture, but I would like to stress this out, this again. We'll have some problems when we want to fully use the cross product, but anyway, we'll get there. Let me draw the picture. So this is a triangle. This is A, B, C. All right, and now I'm gonna draw the following. I'm gonna draw, let's say, A prime in this way, B prime, and C prime. Okay, and here I have 3 points, so it's A1, B1, and A prime, B prime, C prime, and they'll intersect in another 3 points here. And let's call these 3 points, let's say P, Q, and R. Right? And this is the triangle we're interested in. Keep in mind that this is the, right? This is the triangle delta. Is the triangle, in fact, I'll write it PQR. And we want to show that the ratio of the two areas of this triangle and the big triangle ABC, it's this ratio right here, as you can see it. All right. Well, let's look around a bit. And in fact, we would like to write the condition again. So keep in mind that AB prime, so let's keep in mind that AB prime over B prime C is the same as BC prime over C prime A, and is the same as AB prime, is the same as CA prime over A prime B. And this is K. This is a constant K, it's a positive constant. All right. Now, what I would like to do is, the first information I would like to get is the following. I would like to get some information about this ratio here. BP over B prime P. So if I get any information about this, then maybe I could come up with something. Maybe I can express a certain vector. But before we even start doing any computations, let me set up the record straight. And I'm going to consider here the point O, which is the origin of the axis, which will be, well, imagine this is a circle. This O, let O be the origin of the origin, right? And this O, keep in mind that O, where O is the the center of the circumcircle, right? Okay, and we know that this OA, OB, and OC, these are the radius, right? Okay, now we would like to express this ratio because I would like to compute these vectors. I like to compute these like OR OP, and of course OQ. So I like to express these vectors, and it will be convenient for me to express them in terms of OA vector, OB vector, and OC vector. All right, keep in mind the picture. We'll get back to it anyway. The picture is not the most fortunate picture, but I think you can understand it. Okay, now so we would like to get some information. So we would like to get some information about BP over B prime P. So this is our main concern at this point. All right, let's look at this. And we have to look at the picture very, very carefully. How do we get the information about this? Well, let's look in this triangle. So consider the triangle. In fact, let me consider the triangle ABB prime. ABB prime. And here we will have the transversal. What transversal do we have? We have AB prime C, right? With transversal AB prime C. All right, so our intention is to apply Menelaus theorem. By Menelaus theorem, we have, and let's look at the picture. So we will have, imagine that C is inside, so when we'll start from B prime, so we will have B prime C over CA, B prime C over CA times, so now we're at A, AC prime over BC prime, BC prime times, and now BP times BP over B prime P. Which is exactly what we want to do. We know that this is 1 by Menelaus' theorem. Now we look here, look at this guy here. So it's exactly what we want. So we want to get this guy. Well, let's look. B prime C over CA, well, we have to compute this a bit. And we already know AC prime over BC prime. This guy is K. But now this guy here can be written as what? Well, you can flip it, and well, you can say that. In fact, you can say that that CA over B prime C. Well, CA is nothing else than AB prime plus B prime C over B prime C. And now this guy is AB prime over B prime C plus 1. But A prime B over B prime C is K. So this is nothing else than K plus 1. So this would be, so from here, it follows this will be equivalent with, so I have to flip this one, right? So it will be 1 over K plus 1 times K times BP over B prime P, right, is 1. Okay. All right. So that's AB prime over B prime C. Let me check. AB prime over B prime C. All right. So this would be nothing else than B C prime C, AC prime BC over B prime C. So this implies that BP over B prime P is the same, is equal to K plus 1 over K, which is 1 plus 1 over K. Okay. Okay. All right. Okay. Well, I think it's a mistake here. This is 1 over K, not K. And now we're going to have the following. Let me just look around. So this would be 1 over K plus 1. Yes, indeed, this is a mistake here. Let me be clear. Okay. So we will have that. This will be 1 over K plus 1 times 1 over K. So now this implies that BP over B prime P is K times K plus 1. So this is the ratio, right? If we go back the picture, this is the ratio. All right, now analogs. You can write the analogs of this. They will be the same. You can write CQ over C prime Q. So similarly, we have, well, let's look at the picture. We have AR over A prime R. AR over A prime R is K times K plus 1. And we also have that CQ over C prime Q is K times K plus 1. Okay. So we have all these ratios here, but now we're interested, we would like to compute OP vector. So let's see, OP vector will be what? Will be, well, let's look at the picture again. OP vector, if will be, and we would like to write this in terms of OB and OB prime. Look here. So it will be OB vector plus K times K plus 1. It will be OB vector plus K times K plus 1 OB prime vector. Everything over 1 plus K times K plus 1. All right, great. But now let's see who OB prime vector is, and let's look around. But OB prime vector, but now we look in this triangle, AOC, we also have, it's OA vector plus K, so it's OA vector plus K times OC vector over 1 plus K, right? Okay. And now we will plug this in here. And then we have the following. We will have that OP vector. Let's write it here. It will give us that OP vector. It will be, well, I'm just going to skip through computations and everything. I'm just going to say it what it is. It will be, you'll have this constant out, 1 plus k squared times KOA vector plus 1 times OB vector. Let me write it in this way because it will be important. I'd like to emphasize something later on. Plus k squared OC vector, right? Well, similarly, you can do it in a similar fashion. We also obtain OQ vector, which is 1 plus k squared times k squared OA vector plus k OB vector plus 1 times OC vector, and OR vector, it will be 1 over 1 plus k squared, and this would be 1 times OA vector plus k squared times OB vector plus k times OC vector. Okay, so we have these three relations. Now, we would like to compute the area. So the main question is, what about the area of the triangle PQR? Well, you can write this, like I said in the lecture, as RP vector as OP vector by using the triangle rule. You can write this as OP vector minus OR vector, but good luck with the computations. It will be a mess, and then you try to do the cross product. Anyway, I would not like to do that, but if you're fine with it, go for it. There is no problem. And when you compute the cross product, everything, the computation will be just a mess. So I would like to not to do that, honestly. Well, like I said in the lecture, I wish you good luck with the computations. If you want to do them, be my guest. What I want to do right now, just look at these vectors, OP, OQ, and OR vectors. And let's remark something here. Well, like I said, I want to make my life easy, and I would like to introduce something. And that's something that I would like to introduce is the following. It's what we call the barycentric coordinates. And you'll see that they're related to vectors somehow. So let's introduce this, and let me explain a bit. Barycentric coordinates. So instead of me going all the way with vectors, I'll avoid them. I'll stop here because, like I said, I don't want to go into this, like doing messy computations. I don't like to do that. And I plan to, I want to do something that's faster and smarter. So what I would like to do is the following, is to introduce the barycentric coordinates. And in fact, what I would like to say, let's see first, what are barycentric coordinates? Well, and we would like to identify for each point, as you can see here, because I fixed the origin at the point at O, I can identify for each point P, Q, and R, I can identify their barycentric coordinates. Let's see what they are, first of all. So barycentric coordinates are triples of numbers. So these are triples of numbers, let's say. And the way we identify this triple of numbers, let's say, okay, I'm going to T1, T2, and T3, right? This triple corresponding to masses, okay, and I will explain immediately what this means, corresponding to masses placed at the vertices of a reference triangle. Let's say, no, wait, let me call generically this triangle A1, A2, and A3. All right. And let me explain what this masses mean. And you'll see that we can identify from certain points, special points in the triangle, we can identify their barycentric coordinates. These masses determine a point P, right, which is the geometric, centroid of the three masses, and is identified with coordinates say T1, T2, and T3, right? All right, the vertices of the triangle are given by, usually the vertices of the triangle are given by, and we're gonna say it in this way, by 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? So this is how we're gonna operate with barycentric coordinates. In other words, we will assign to each vertex of the triangle with the we will assign the barycentric coordinate 1, 0, 0 to the first vertex, then 0, 1, 0 to the second, and then to the third 0, 0, 1. Well, I would like to say the first one who actually discovered this, in fact, he applied them in a much more general setting, was Mobius back in 1800s. So also I would like to say that barycentric coordinates are homogeneous. So So one can have something like this, like with this triple T1, T2, and T3. This will always be equal to, let's say, lambda T1, lambda T2, and lambda T3 for lambda non-zero, right? Well, we can also normalize this. Well, keep in mind that these barycentric coordinates here, if you well, let me say that barycentric coordinates can be normalized Well, this means that so that, and I will explain a bit, so that they can become, so that they become the actual areas of the subtriangles, of the subtriangles and they are called homogeneous barycentric coordinates. Okay. So they can be normalized in such way, let me mention this, they can be normalized such that these numbers, such that T1 plus T2 plus T3 will be 1. Okay, and now let me just mention some of the barycentric coordinates. For example, if I have the triangle with vertices, like I said, 1, 0, 0, 0, 1, 0, and 0, 0, 1, well, guess what? The triangle centroid will have, so G will have the barycentric coordinates, well, 1, 3, 1, 3, and 1, 3, right? Since we normalize this, for example, because you know that also this comes from the fact that 3 OG vector, so you can associate this guy with 3 OG vector is, or maybe I should write it in this way, OG vector, this is 1/3 OA vector plus 1/3 OB vector plus 1/3 OC vector. So this is where you're getting this, right? For example, I will have the barycentric coordinates, let's say A over A plus B plus C, B over B, A plus B plus C, and C over A plus B plus C. Anyway, these are already normalized here. As you can see, I wrote them in this way. So these three add up to 1, or you can associate this to OI vector if you want, because I think I mentioned this in class, is A over A plus B plus C times OA vector plus B over A plus B plus C times OB vector plus C over A plus B plus C times OC vector. Anyway, and you can keep going, etc. Sometimes they're just in terms of, well, I'm already normalizing them so that everything will be, so that we can have this, they will add up to 1. Sometimes instead of G, they're put 1, 1, 1, and here instead of A plus B plus C, they are like, the in-center has A, B, and C. But anyway, it doesn't really matter that much. Okay, now let's get, there is a thing here that I would like to talk about. So we have the following lemma, which I will not prove, but this will be useful for our problem because we would like to express, now I'm going to barycentric coordinates, and I would like to express the area of my triangle PQR because I already know the barycentric coordinates at this point. So the lemma says the following. Let P1, P2, P3 be points with barycentric coordinates and let's just say this is with reference to triangle ABC, right? And let's just say that PI, these 3 points, have the barycentric coordinates, let's say UI, VI, and WI. And this I is 1, 2, and 3. And then the signed area of the triangle P1, P2, P3 is given by the following formula. It's given by the following determinant formula. So this will be, let's say, the area of the triangle P1, P2, P3 over the area of the triangle ABC. This will be nothing else than just this determinant formula, U1, V1, W1, U2, V2, W2, and U3, V3, W3. All right, so that's the lemma. This is the formula. And now guess what? Let's go back to our problem. Going back to our problem, we have, and let's see. Let's look, what do we have? The barycentric coordinates, keep in mind we have this here. Well, we can say that they're like K1, but we can take that into account. So it will be so let's see. So we have that the area, we have that the barycentric coordinates of P are, let's look again. They're K1, K squared, and K1, K1. Okay. Q will be, what was Q? I think it was K squared, K1. Okay, and then the last one was 1 over K squared plus K plus 1. And the last vertex was, let's see, what did we have? I think we had 1 K squared K, okay. Oh. Okay, so now we have these 3 points. And now we're trying to find the area. So the area, so by the lemma, we have that the area of the triangle PQR over, which is delta anyway, over the area of the triangle ABC is nothing else than just the determinant of these guys. So we will have P1, okay, I'll put here K over 1 plus K squared, 1. Okay. And the last row will be 1 over k squared plus k plus 1. K over k squared plus k plus 1. All right, well, it's quite clear we can factor something here. So we will have that this is we can factor 1 over k squared plus k plus 1, everything cubed, times this determinant, k1, k squared, k1, 1, k squared, k. Well, the determinant of this, well, I'll leave it to you as an exercise, since I don't want to compute this. This is a easy determinant. If you learn how to compute this in any linear algebra course. Well, if you didn't take any linear algebra course, I will invite you to go to one of my videos in my linear algebra class that I taught this summer. I think it was maybe lecture 3, I think, video number 3. Okay, videos 3, 4, something like this. You'll find them on YouTube. Well, at some point, this guy will give me exactly k minus 1 squared over k squared plus k plus 1. And that's it. That's the problem. Anyway, that was briefly, there is a whole theory of the barycentric coordinates. Like I said, I don't want to go into this too much. Like I said, if I spend time only on geometry to go as in detail as much as I can, probably it will take me as a semester. Already took us a couple of lectures to cover the most basic things, I would say, in geometry. All right. Well, like I said, I tried to avoid heavy computations. I didn't want to do any of them. But now, well, I want to show you an example, a very similar problem. It's unbelievably similar. So problem 2 says the following. And you'll see how similar this is. In fact, I would say that this is a bit, I want to say simpler, but they're very similar. This was a Putnam A4 in 2001, so not that long time ago. And the problem says the following. Triangle ABC has area 1. Points E, F, G lie respectively on sides BC, CA, AB such that well, AE bisects BF at point R. So it's even a little bit more particular, this one. BF bisects CG, will bisect BCG at point S, and CG bisects AE at point T. And now the question is, find the area of triangle RST. That's the statement of the problem, right? I want you to look at it. It's very similar, but in fact, I would like to draw a picture so that things will be clearer than this. And the picture is the following. All right, let's draw the picture. Here we go. So we have the triangle ABC. This is ABC. And let me draw this. This will be AE. This will be BF. And CG. And here we'll have R, here we'll have S, and here we'll have T again. So I'm interested in finding the area of this triangle here. You see, it's the same, basically the same picture. The only difference is that we know that the AE bisects BF. Well, anyway, and the others as well. All right, so this time I will avoid barycentric coordinates. I want to do it the hard way because I want you to see a fully use of vectors in this problem. It's a very nice problem. Okay, and now let's look. Let me look at, you see these vectors BE and BC are collinear, so we can say that, well, let BE vector, so we're gonna start from B, our orientation goes from B to C, it will be some number, let's say constant X times BC vector, and also we have the analogs as well. CF will be a Y times CA vector. Keep in mind that with the orientation here. And also we can say that AG vector, we want to keep the same orientation, it's some constant, let's say Z times AB vector. All right, so we have this. Now, all right, now we're going to do the following. Let's look in this triangle because I would like to express AB vector in terms of, okay, let's look at this triangle. ARB. Look at this triangle, right? So in the triangle, let's write it here. ARB, we apply the triangle rule or Charlotte rule, and we get what? Well, let's be careful here. We have that A, okay, we're going to start from here. So AR plus RB is the same as AB. AR vector plus RB vector is the same as AB vector. Or equivalently, we can write this as AR vector is AB vector minus RB vector or plus BR vector, right? So we have this. And now we can express this in the following way, BR. Moreover, we have that AR vector is the same as AB vector plus, now let's see, BR vector, let's be careful here. BR, where is it? All right, BR vector. BR vector is it's 1/2, all right? Yes, it's 1/2 BF vector. Keep in mind that we said that AE, right, bisects BF at point R. So this would be 1/2 BF vector. But now we can write this in the following way. It's AB vector plus 1/2 times, and now I can write the BF vector as okay. Now so I can write this as, let's see. So BR will be BF, sorry. Okay. ABB, okay. So it's BC, that's BF vector. Okay, so it's BC vector plus Y times CA vector, right? Keep in mind that BF, you can write it as, well, you see this is CF vector. So BF vector is BC vector plus, so BF vector is, you look in this triangle. Okay, let me explain this. You look in this triangle now. You apply the triangle rule. You have the triangle BFC, and you have that BF vector plus FC vector is the same as BC vector, but you know that CF vector is Y times CA, and then you just write it in this way. Anyway, you will understand what I mean by that. All right. Beautiful. Let's keep going. We have to be careful here. Oh my, there are some computations. All right. Okay, we have to be careful here because now at this point we only have like A, B, B, C, and CA, which is great. So we have to keep going. And this will be equal to AB vector plus. And now let's be careful. Yeah, we can use the triangle rule for the CA in the big triangle. So this would be 1/2 times BC vector plus Y times, and now CA vector. So CA vector, so it will be AB vector plus BC vector will be AC vector. So this would be a minus. We'll take a minus is outside, right? Okay, let me write like this, and then I don't want to, let me do a step by step. So CA vector is, so it's A beam, so it's minus AB vector plus BC vector. If you want, this would be AB vector plus 1/2 BC vector minus Y times AB vector plus BC vector. Okay, this looks nice. Great. And now if we do all these computations here, this would be equal to, and we know each one what it is. Yeah, we already know. So this will give us, AR will give me something like, okay. All right, so this will give me 2 minus Y over 2 times AB vector plus 1 minus Y over 2, everything over 2 times BC vector. All right, finally. Whew. So AR vector is, we can write it in this way. So let's write it again. So AR vector is 2 minus Y over 2 times AB vector plus 1 minus y over 2 times BC vector. All right, that's good. Also, let's keep in mind the following, that also, now I want to use the following, that AE and AR are parallel as vectors. So in other words, now maybe I can write AE vector, and of course I can do it because AE will be also by the triangle rule. And ABE. If we apply the triangle rule in triangle ABE, we have what? Let's see. ABE, let's look at it. We have that AE vector plus EB vector. Okay, let me look again. AE vector plus EB vector is the same as AB vector. Or EB, okay, or you can say that AE vector is the same as AB vector minus or plus BE vector, right? It's minus EB vector, or you can say plus BE vector. All right, great. But BE vector is, let me go back again, BE vector is X times BC vector, if you look, right, at the beginning. So this will be equal to AB vector plus X times BC vector. Okay, we have this. Since AE vector and AB are parallel, we have, guess what we will have? Well, this X here will have to coincide. So this X from the BC vector, as you can see here, I expressed, sorry, AE and AR, not AB. Oh my, it's late. This is AR here. Since these are parallel, then if you look at the coefficient here of BC, this is X, right? And look at the coefficient of AR of BC, which is this guy. So this implies that these two should be equal. We have that 1 minus y over 2 is the same as X, right? Wait, what am I saying? Jesus, no. X is proportional to that. So X over 1, yes, X over 1 will be equal to 1 minus y over 2 minus y over 2. So it will be 1 minus y over 2, 1 minus y over 2 minus y. So X is nothing else than just 1 minus y over 2 minus y. All right, so we have this relation here. Well, similarly, or we can say by symmetry, we have that. What do we have? We have that y is the same as 1 minus z over 2 minus z, and z is 1 minus x over 2 minus x, right? So we also have these relations. Well, I'll leave it to you, but solving this system, it's actually a system of equations. Solving this, it will give us that x is equal to y is equal to z, and it will give us something like, yes, 3 minus root 5 everything over 2. Well, according to my computers. Oh my. So this is how we now. So this is how we compute the AR. So we'll get some information by doing this. But now what we want to do is to compute these vectors, because keep in mind, I'm interested in these vectors in this triangle, right? In this triangle STR. So it's good for me to compute two vectors joining one vertex, right? Let's say ST and SR, or TS and TR, whatever. And we would like to see to compute the cross product of these two vectors. But anyway, we'll get there. First, let's compute now let's compute TR vector. So TR vector now will give us what? By the triangle rule, it will be nothing else. So you apply the triangle rule in the triangle, let me see, TR. So this would be, we don't even have to apply any triangle rules there. So this will be AR minus AT, right? And this will be nothing else. We know AR. So this will be AB vector plus 1/2 BF vector minus 1/2 AE vector, right? And this will, if we keep going with computations, this would be AB vector plus 1/2, and now let's be careful, BF vector is a BC vector plus Y times CA vector. All right. And now minus 1/2, and now let's write AE vector. This will be AB vector plus C times BC vector. Oh my, yeah, okay, right? Okay, now, so we know TR vector. And now if we do all these computations together, this will give us since I know I have everything here, okay, this will be similar. This will be 1 minus 2, 1 minus y over 2 AB vector plus 1 minus x minus y, everything over 2 times BC vector. Okay. All right. So we will write this, and so we wrote this vector TR as 1 minus y over 2 times AB vector and plus 1 minus x minus y over 2 times BC vector. And now we can keep going because we can we can do some computations here, right? Because we know that x and y are equal. So this will be equal to, let's write it in this way, 1 minus x over 2 times AB vector plus 1 minus 2x everything over 2 times BC vector. Okay, that's nice. And, oh, right. So we have used here, I would like to say that shell rule, that AB, so we have used that, use the triangle rule. Which is AB vector plus BC vector, which equals AC vector, or plus CA vector is 0. Anyway. All right, now, again, by symmetry, what do we have? We have that RS vector is nothing else than just 1 minus x over 2 times BC vector plus 1 minus 2x over 2 times CA vector. And if you want, you can write this in the following. Again, using triangle rule, you can write this as negative, if you want, 1 minus 2x over 2 times AB vector plus x over 2 BC vector. Okay, so we can do that. And now finally we can use the cross product formula. Finally, the area of the triangle, let's say RST, is nothing else than just 1/2, right? Keep in mind that the magnitude of the cross product of two vectors is the magnitude of the vectors times the sine of the angles between them. So in other words, this will be nothing else than just the magnitude of TR vector times RS vector. And this will be, if you know how to relate this, this will give us something like, well, I think I've done the computation somewhere. Okay, let me see. So this would be 1 minus 3x plus 4x plus 3x squared, everything over 4, right? Times 1/2, let's not keep in mind, times the magnitude of AB cross AC. Well, we know who, which is, let me point this one out. We know that this is the area of the triangle ABC. And we know that this area is 1. So this would be nothing else than just 1 minus 3x plus 3x squared, everything over 4. And this would be nothing else than just, well, if you know who x was, and at some point, if you plug them in, after some computations, this will give us 7 minus 3 root 5, everything over 4. And that's the value. And that's the end of the problem. Whew. All right, so we spent a lot of time on these two problems, but I wanted to do it anyway, because these are very nice problems. And I would like to do one other problem, which was in a worksheet. And let me look for the worksheet. It was problem 20 in the worksheet, and says the following. So let's see, problem 3. And this was not a Putnam problem, but it was similar to a Putnam problem given last year or 2 years ago. No, last year, actually. This was a Romanian National Math Olympiad, I think, in 2005. Anyway, it's a pretty standard problem, which says the following. Let ABC be a triangle inscribed in a circle of center O and radius R. Let I be the incenter of ABC, and let R be the in radius of the same triangle. Okay, O is different than I, and let G be its centroid. All right, the problem asks us to show that, prove that, it's actually if and only if, IG is perpendicular to BC, well, that's a huge information at this point, if and only if, so if it's if and only if, B equals C, so the triangle is isosceles, or B plus C equals 3A. So that is the problem. Let's look at the statement. It's a pretty nice problem. At some point when I will discuss, well, at the end of the course, one of the lectures will be to the discussion of the Putnam problems over the last 2 years. And one of the problems given, I think last year or 2 years ago, I don't recall exactly, but for sure it's a very, very recent problem. It's very similar to this one. Basically, it says that what happens if IG is parallel to, well, to one of the sides of the triangle. But I think it was AB. Anyway, it doesn't really matter. The procedure is the same. You can solve this problem without the use of vector geometry. I think the official solution was like that, but I prefer to do it using vector geometry. And let me remind you that we have a bunch of relations that I told you, right? For any point M in the plane, we know that MA vector plus MB vector plus MC vector is 3MG vector. And also, and we actually proved this, and I told you that you similarly, and we also have that A times MA vector plus B times MB vector plus C times MC vector is A plus B plus C times MI vector, right? So we said this. We proved the first one, and the second one, I told you it's very similar in nature with the first one. All right. Ooh. Let's see. Let's draw the triangle. I think it's easier to see a picture here. We have A, B, C, the triangle. Let's draw a bisector. So this is the bisector. Somewhere here on the road is I. And let's draw the median. Let's say here. Somewhere here on the road, let's say it's G. And we want to see well, maybe I should put it somewhere so that I don't know, it will be somewhere. Let's put it, oh, let me draw it again. In fact, no, let me draw the okay. So we will draw in such way that this guy, this is the I will be some anyway. So imagine that I will have somewhere here I, and G will be somewhere in such way that this guy is perpendicular, will be perpendicular to this guy anyway. I'm not some right to BC. All right. Okay. All right. So now what we're going to do is the following. Well, it's pretty vector. We can use vectors. And let me remind you something. That something happens when this is true, when I have this, right? So, but before I even go and touch it, this, let me remind you that I can compute a G vector. I can compute this guy. And I can also compute AI vector. I can compute this guy as well. Okay, let's do it. AG vector, and you know, this is the median. Here, actually, let me put here, this is D and this is A1. You know, the median, just look here. You know that AA1 vector is 1/2 so we know that A1 vector is 1/2 times AB vector plus AC vector. All right, great. But we know that AG vector is 2/3 of AA1 vector. Well, from here, it follows that it follows what? It follows that AG vector is 1/3 times AB vector plus AC vector. All right, the same scenario will hold true, but it will be a little bit different now. So I'm going to do the same thing here. Look here. I know that, but here I have the bisector theorem. You know, the ratio is similarly. We have that, well, you know that AD vector is AB vector plus this number k, and we'll determine what this is, times AC vector times 1/1 plus k. And this k, where k is given by BD over DC. All right, but you can apply the bisector theorem here. Look here. Look, this guy over this guy is the same as this guy over this guy. Oop. All right, so it will be BD over DC is nothing else than just AB over AC. Or with the standard notations for the triangle, this would be C over B. So this will imply that, so AD vector is AB vector plus C over B AC vector times 1 plus C over B. Anyway, and this will give us, I'm going to write it directly, now you can do the same trick in this triangle here. And I'll leave it to you as an exercise to do it. It's actually quite easy. And keep in mind that now this guy BI is the bisector. So I do the same trick. I apply the bisector theorem because I want to know the ratio between AI and ID, because I want to express BI vector, right? Right. Because I want, yes, I want to compute AI vector. So yeah, but anyway, I'll leave it to you. And we also have that AI vector. So similar, you use the same strategy as for G. It will be B times AB vector plus C times AC vector and everything over A plus B plus C. Okay, so we have these two equalities here. This one. And we also have, where is it? This one. Look at these two. Look at that. All right, and now guess what I'm going to do? I will look at the triangle AIG, and I'll apply the triangle rule. Applying the triangle rule in the triangle AIG, we have, what do we have? So we can express the vector IG. Well, let's look. It's AI plus IG equals AG. So IG vector will be nothing else than just AG minus AI. All right. And once we do all these computations here, oh my, we have to subtract these two. And after we do all this, you know what, I'm not gonna do the computations. I have them somewhere here. I've done them already, so I don't wanna. So this will give us the following, okay? So we'll have a common factor, 1/3 times A plus B plus C times, and we have the following. We have A plus C minus 2B times AB vector, right? Plus, the other one will be A plus B minus 2C times AC vector. Okay, great. But now, guess what? So I expressed a EIG vector. At this point, I know what's going to happen. So IG is perpendicular to BC if and only if the dot product between IG and BC is 0. So we want to use this. We know IG, you see it. And now, let's see. There is one more thing here, one more trick, but IG vector dot BC vector, this will be nothing else than just IG vector. Well, you can apply BC vector. BC vector is apply the triangle is nothing else than this AC vector minus AB vector. So this will be equal to IG vector times AC vector. This is G here, minus IG vector dot AB vector. All right, great. And this will be, if you this will be, oh my, if we have again some computations, and this will be equal to IGAC, so this will be 1/3 times A plus B plus C times, and now here we go again. So IG, so it's A, B, A, C. Okay. Okay, maybe I should say, all right, I'm gonna copy exactly the, so this would be equal to, let's see, and then I will explain immediately my computation. So this will be, all right, so this will be A plus B minus 2C times B squared minus A plus C minus 2B times C squared plus 3C minus B, and I will here B squared plus C squared minus A squared over 2. That's it. Okay. And after some computations, this would be equal to, all right, some computations here. I'll leave it to you as an exercise to see this. This will be equal to 1/6 times C minus B times B plus C minus 3A. Great. All right. Well, keep in mind, here we have used the following fact, and I'd like to address this. Here we use the fact that, in fact, let me explain it here. Here we use the fact that AB vector dot AC vector, this follows from the cosine law, is nothing else than just b squared plus c squared minus a squared, everything over 2, right? So we have used this, and at the end I got this this here. Well, at this point I think it's quite clear. We know that IG is perpendicular to this if and only if, so we have this. And now this implies that this should be equal to 0. So we have that what? We have that this guy, 1 over 6, c minus b times b plus c minus 3a is 0, which is equivalent with b equals c or b plus c equals 3a, which is exactly what we wanted to prove. And that's the end of the problem. Okay. I would like to solve 2 more problems, and in fact, just like sketch them because they're quite easy. They're from the worksheet. Where is it? The first one was problem, so this would be the 4th problem for today. And it's problem 16 on my worksheet, and it says the following. It's a Putnam A2. It's an old one, but it's a very nice one. 1966. You'll see, well, in these next 2 problems, I'd like to solve some geometric inequalities. So that you can grasp more techniques about how to solve these type of problems. Let ABC be the length of the sides of a triangle. And let S be the semi-perimeter, which is given by a plus b plus c over 2. And R be the in radius of the inscribed circle. Show that 1 over s minus a squared plus 1 over s minus b squared plus 1 over s minus c everything squared is greater or equal than 1 over r squared. All right, so that was the problem. Let's look at the statement. Well, you can do this in many, many ways. But let's, we had something similar, I think, in the first lecture, I think, and I didn't quite finish the problem. I just told you how to solve it. But this one here, if you look at it, let's look at it. We know how to compute the in radius, right? If you look at it, R, we know that R is S over S. Oh, it's the area. Okay, you know it by K. It's K over S, the semi-perimeter, right? Okay, but also this could be, so from here, R squared is K squared over S squared. Or if you want to apply Heron's formula, or R squared will be S times S minus A times S minus B times S minus C over S squared here, right? S will go away. So this is S minus A times S minus B times S minus C, everything over S. All right, great. So our inequality is equivalent with the following. So the sum, let me write it in with cyclic sum of 1 over S minus A squared will be greater or equal than 1 over that, which will be S over the product of S minus A. And this will be equivalent, if we do some computations, this will be nothing else than the cyclic sum of S minus B times S minus C, everything over S minus A, greater or equal than S. And now guess what? Let's do the following substitution, S minus A being, it's an X. Well, let me show you let me do the computation. So this is A plus B plus C over 2 minus A. So this would be B plus C minus A, everything over 2, right? And let's denote this by an X. And in fact, we don't even need to do that. So denote S minus A by an X, S minus B by an Y, and S minus C by a Z. Keep in mind that this is nothing else than just, okay, I'm going to say it. So it follows that what? It follows that, or we can say that the inequality reduces to what? The cyclic sum of xy over z greater or equal than the sum of x. Or if you do the computations here, if you want to, anyway, you can solve this inequality in many, many ways. For example, you can just apply AM, GM 2 by 2. Okay, let me do it this way. By AM, GM. We have that, let's say, xy over z plus, let's take another one, y z over x is greater or equal than 2 square root of xy over z times yz over x. And this will give us, if you look here, some things will cancel, be 2y. And you write the analogs plus the analogs, and you add them up, and that's it. All right, that was the problem 16 from the worksheet. And I have one more problem to discuss, and maybe I'll leave it to you. Oh, man, it's been a bit long. And the next problem, which is problem 17, and it will be problem 5 in our discussion here, was in fact, this was a Putnam problem. Was a Putnam, let me look. It was a problem, Putnam A3, 1971, a bit old, but anyway, still a nice problem, which says the following: the 3 vertices of a triangle of sides A, B, and C are lattice points. I think we have said a few things about these at this point. lattice points, points of integer coordinate with their coordinates being integer numbers, and lie on a circle of radius r. Show that, again, a geometric inequality, show that ABC is, their product is greater or equal than 2 times r. All right, well, this is pretty straightforward at this point. And in fact, I'm going to leave this to you. I'm just going to say the way, well, remember we have this formula. In fact, we're trying to reduce everything to this one thing. Remember that that the circumradius, right, r is ABC over 4 times the area. So from here, it follows that ABC is nothing else than 4 times k times r. So our inequality is equivalent with what? With 4kr greater or equal than 2r, or you can say that k is greater or equal than 1/2. So in other words, it says that if you have a triangle with its vertices, lattice points, then its area is at least 1/2. Well, I'll leave this to you to this to prove. But the only thing I could tell is to look for Pick's theorem. I'm just gonna say try to Google it. Well, in fact, Pick's theorem says even more general. If you have a polygon and its vertices are lattice points, then you can compute the area of the polygon. And it has this formula. So basically, this formula can be determined just by counting the lattice points on the interior and the boundary of that polygon. And that's it. And you'll see that it will, in fact, the area will be something like, okay, let me say it. And with that, probably I'll end up here. So Pick's theorem says the following. So it says that let P be a polygon in the plane whose vertices have our lattice points. Okay. Then the area of P, of our polygon P, can be determined just by counting just by counting the lattice points on the interior and boundary of the polygon. Of P. Okay, keep in mind this. And in fact, we have the formula, the area of P, area of P is given by this formula. It's I plus B over 2 minus 1. And let me explain each one of them what it is. So this is the formula of a polygon. And in particular, you can compute for a lattice triangle. This I is the number of interior lattice points. and this B is the number of the boundary lattice points. Yes. Anyway, the number of lattice points on the boundary is the same thing. Lattice points. And from here, I'll leave it to you to show that if I have a triangle, then the area is at least 1/2. Anyway, I'll leave it to you as an exercise that to show, and that would be it. Okay, I think it's a good place for me to stop now. Thank you very much. Next time, next week, we will start talking about combinatorics, and you will see a bunch of techniques there as well. Such as we'll go back to binomials a bit because I did not mention them. We'll talk about counting. Maybe a bit about graph theory, but also I would like to stick to something more basic at first, which will be the pigeonhole principle. Okay, thank you very much. I'll stop here.